We've already looked at a carbon-hydrogen bond, and in the last video we actually calculated an approximate wave number for where we would expect the signal for a carbon-hydrogen bond stretch to appear on our IR spectrum. And we got a value of a little bit over 3,000 wave numbers. However, that wave number depends on the hybridization state of this carbon. So let's look at some examples here. So if we look at an example where the carbon is sp hybridized, right? So we know this is an sp hybridized carbon because we have a triple bond here. So we're talking about a carbon-hydrogen bond where the carbon is sp hybridized. The signal, right, the signal for this carbon-hydrogen bond stretch shows up about 3,300 wave numbers. If we look at this next example here, so now we have a carbon that has a double bond to it, so it must be sp2 hybridized. So we're talking about a carbon-hydrogen bond where the carbon is sp2 hybridized. The signal for this carbon-hydrogen bond stretch shows up about 3,100 wave numbers. And then finally, if we look at a situation where we have only single bonds to this carbon, we're talking about an sp3 hybridized carbon here. So we're talking about a carbon-hydrogen bond where the carbon is sp3 hybridized. The signal for this carbon-hydrogen bond stretch shows up about 2,900 wave numbers. And so how do we explain these different wave numbers because they're all carbon-hydrogen bonds? Well, we need to think about the hybridization. So let's do that. So if we look at the sp hybridized carbon, remember that means that this carbon has two sp hybrid orbitals. And an sp hybrid orbital, right, has the most s character out of all these orbitals that we've discussed here. So it actually 50% s character, if you remember that from the videos on hybridization. So 50% s character for an sp hybridized orbital. For an sp2 hybridized orbital, it's about 33% s character. And finally, for an sp3 hybridized orbital, it's about 25% s character. And so going back to the sp hybridized carbon, right, so the sp hybrid orbital is 50% s character. That means, remember what that means, the electron density, right, is closest to the nucleus. So if that's the case, then we're talking about this bond right here, this bond being the shortest bond because the electron density is closest to the nucleus, the more s character you have. And if this is the shortest bond, it must be the strongest bond out of these three that we're talking about. So this carbon-hydrogen bond where the carbon is sp hybridized is stronger than the carbon-hydrogen bond where the carbon is sp2 hybridized. This bond, though, has more s character than this one, so this bond is stronger than this one. And so this order of bond strength explains the wave numbers, because if you remember from the previous video, right, the bond strength affects the force constant or the spring constant K. So as you increase in bond strength, you increase K, and we saw that increasing K increases the frequency or the wave number, right? So this increases the frequency of bond vibration or increases the wave number where you would find the signal on your IR spectrum. And so since this is the strongest bond, right, this is the highest value for the wave number. So we're going to find this signal, right, more to the left on our IR spectrum when we're looking at it. All right, now that we understand this idea, so the hybridization, we can look at some IR spectra for hydrocarbons and we can analyze them. So let's do that. First, let's compare alkanes and alkynes. So let's go down here and let's look at some spectra. So let me just pull down here and we can look at two IR spectra. The first one is for this molecule, which is decane, so hopefully I have the right number of carbons drawn there. The second one is for one octyne, so a triple bond in this molecule. Let's compare these two to think about the differences. All right, one of the things that's sometimes helpful to do is to draw a line around 3,000. So let me draw a line around 3,000. I'm going to try to draw it for both here too. So I'm going to draw a line around 3,000 for both, right? So we can compare these two spectra. All right, we know that a carbon-hydrogen, let me go ahead and write this in here, a carbon-hydrogen bond where the carbon is sp3 hybridized, right? So that signal for that stretch shows up under 3,000, and so that's why it's helpful to draw a line around 3,000. So that's what we're talking about when we're talking about this complicated looking thing in here. All right, so it's not really worth your time to analyze this in great detail, and of course my drawing of the isn't perfect to begin with, but think about under 3,000, right? That's where you expect to find your signal for your carbon-hydrogen bond. We're talking about an sp3 hybridized carbon. And those are the only types of carbons that we have in decade. And so if we think about the diagnostic region versus the fingerprint region, right? So if I draw a line here to separate those two regions, in the diagnostic region, all we have is this, right? So all we're thinking about is carbon-hydrogen, and the carbon is sp3 hybridized. So a very simple spectrum to analyze. When we move on to 1-octine, so now we're looking at this one down here. Right, so we see that same kind of thing, right? Because obviously we have carbon, hydrogen, sp3 hybridized, right? Also in this molecule, and so this isn't going to really help you too much when you're analyzing spectra, but it's useful to know what you're looking at, drawing a line at 3,000 and thinking about that's what that represents. All right, so once you draw that line of 3,000, it allows you to see some differences, right? So for example, right, this signal right here, if we drop down, it's pretty close to 3,300, right? So this would be 3,100, 3,200, so 3,300, so approximately 3,300 wave numbers. And we know what that signal represents, right? We can go back up to here and we can look at about 3,300 is where we would expect to see this carbon-hydrogen bond stretch where that carbon is sp hybridized. So that's what we're looking at there. So let's go down and look at the dot structure and see if we can figure out what it means on the dot structure. All right, so this signal, right? This signal must be a carbon-hydrogen bond where the carbon is sp hybridized, and that would be right here, right? So we have a carbon here, and then we have a hydrogen right here. We also have a carbon right here, so that gives you your 8 carbons. And so this bond, let me go ahead and highlight it here. So this bond right here, this carbon-hydrogen bond, where this carbon is sp hybridized, that's this signal. That's this signal on our spectra. And so once again, it's useful. It's useful for analyzing here. All right, we have something else that shows up in the diagnostic region for this alkyne, and it's this signal right here. So if we drop down, right, what's the wave number where this signal appears? The wave number is about 2,100, so approximately 2,100, maybe a little bit higher than that. And that's the carbon triple bond stretch, right? So that's the carbon triple bond stretch that we talked about in an earlier video, right? So that's approximately the triple bond region when you're looking at your spectrum. And of course, obviously we have one. This is an alkyne here. And so hopefully this just shows you the differences. And once again, your fingerprint region over here is unique for each of these molecules here. So this shows you the differences and helps you to think about how to analyze your IR spectrum. Let's look at 2 more. All right, so let's look at one more here, and let's compare these two. So now we have a spectrum for an alkene, right? So here we have 1 hexene. And let's see if we can analyze this one. So we're going to do the same thing. We're going to draw a line around 1,500. Right? So draw a line around 1,500. We're going to draw a line around 3,000. And let's analyze this one, right? So we know what this one's talking about. We know this is talking about a carbon-hydrogen where the carbon is sp3 hybridized. All right, but what's this signal right here? Right? We drop down, and that's pretty close to 3,100, right? So that signal is approximately 3,100. And so we know what that must represent, right? That's a carbon-hydrogen bond where the carbon is sp2 hybridized. So that stretch occurs at this frequency or this wave number. And so we know an sp2 hybridized carbon must be present. And obviously here with this double bond, right, we know we have an sp2 hybridized carbon. Notice the difference between this one and the one we just talked about. So let me go ahead and highlight this here. So this signal shows up around 3,100, right? So I draw a line up here, and we saw this signal at 3,300. So it's useful to think about. It helps you distinguish on your IR spectra if you draw a line there and think about where the wave number is. What wave number does this signal appear? All right, we also have something else showing up in this one. Let me go ahead and draw this one in here. So what is this? What is this guy right here? That looks like a pretty obvious signal. So we can drop down here and check out approximately where does that show up? What's that wave number? All right, well, if this is 1,500, this is 1,600, this is 1,700. So that's a little bit. It's pretty much in between, right? It's approximately 16,000 50. Right, and in an earlier video, we said that was in the double bond region, right? So that's the carbon-carbon double bond stretch signal right in here. So, and obviously there's a double bond in our molecule. So this again, comparing these two, remember we talked about the fact that a triple bond, right, vibrates faster than a double bond, and so the signal, right, the signal is different, right? The triple bond vibrates faster, so it has a higher wave number. The double bond doesn't vibrate as fast, so it has a lower wave number. So these are important things to think about. Finally, let's compare this alkene, right, to an arene here. So let's look at toluene right here. All right, so if we do the same thing, if we draw a line around 3,000, right, so somewhere around 3,000, and we know this is below 3,000. Right, so we know that this must be talking about carbon hydrogen where the carbon is sp3 hybridized. That's a carbon hydrogen bond stretch with the carbon's sp3 hybridized. Well, this carbon right here on toluene, right? So this is toluene. That carbon's sp3 hybridized, so that makes sense. We have this one little peak here, this one little signal that's a little bit higher than 3,000. So it's pretty close to 3,100. Right, and we know that's approximately where we would find a carbon-hydrogen bond stretch with the carbon's sp2 hybridized, so somewhere around 3,100 here. And so this makes this. At first, you might think, oh, well, how do we tell this apart, right? So this is very similar. This is very similar to this situation, right? So this looks very similar to this, and so it can be tricky sometimes if you're just glancing at that part of your spectrum. Let's think about the double bond region too. So the double bond region right up here, right? So this is where, if this is 1600, right? That's for this one. I'm gonna draw a line down here, and let's try to connect the 1600s right here like that. And let's think about what happened, right? So here's the signal for the carbon-carbon double bond here. And when you're talking about an aromatic double bond stretch, so carbon-carbon aromatic, right? That's usually shows up lower than 1600. So here it looks like we have two signals, right? So it depends on what kind of compound you're dealing with, but we can see that this usually shows up lower, right? So this is somewhere usually around 1600 to 1450, right? But we're talking about the carbon-carbon double bond stretching here. And there's some other subtle things that clue you in, like this right here, right? So we don't really see that on this spectrum. And then these down here, we're missing those here too. And it'd be way too much to get into in this video to talk about what these mean, and it's a little bit more than we've talked about so far. So that'll have to be a different video. But there are subtle differences, right? And the easiest one is to think about the fact that this aromatic carbon-carbon double bond shows up at a lower wave number, right, than the one that we talked about right here. So just look at the sheer multitude of signals, and sometimes that clues you into the fact that you're dealing with this benzene ring here for toluene. All right, so that sums up just a quick intro to looking at IR spectra for hydrocarbons.